Hey guys, welcome back to TBS Skylabs. We're on the second part of our coding and implementation, which is the making part of our program. And we were making this Yeti language learner, which is, your kind of Duolingo, kind of that sort of thing for saving words and making learning a language. In my case, Nepali, which I'm rubbish at, but trying to learn. Jayo. Okay, so last class, or last video, we looked at the word node, and we started building some of that. We're going to add in more of that today, but today our focus is really going to be on the word tree. Now, realistically, we're not working with big data sets. A linear search would be totally fine, but let's up our game a little bit, get a bit of practice, and make a binary search tree. Well, what on earth is that? Well, a binary search tree is just a way to store things in an ordered way that's going to reduce the amount of time that it takes for us to find it. So in a linear search, we're going to do one by one by one by one by one. Binary search would be better if we had ordered data, but we could actually make a structure called a binary search tree that allows that search to happen much more efficiently. Okay, and this is from Geeks for Geeks over here. Okay, so now I've copied this image down to here. So if I was looking for a number in here, I would come to this first item. And this first item is called the root. Or root node, if you like. Okay, paint is somewhat antiquated, but fine. We've got a root node, which is the first node in our tree. Now, if I were to add or to be looking for something inside the tree, let's say I'm searching for a 6. Okay. I'm going to be searching for a 6. So what happens? Well, my this one over here. So I take the 6 and I compare it with the first node. And first of all, I say, is it equal to this number? If the answer is no, then I have to say, well, is it bigger or smaller than this number? So in this case, 6 is smaller than 8, so therefore I go to the left. However, if it were, say, 14, I would go to the right. Now, when I go to the left, what do? Well, I repeat the same process. I say, is it equal to the current node? Nope. If it's not equal to the current node, then is it less than the current node? Yes. Sorry, no, it's not. Sorry, big stupid. So 6 is not less than 3. Is it bigger than the current node? Which it kind of has to be, really, because we've said it's not the same and it's not less than. But yeah, but for simplicity's sake, is it greater than the current node? Yes. Well, then we pass it down to the node on the right. Is 6 equal to 6? Yes. Okay, therefore, it does exist on our tree. Now, what about if we had a number that didn't exist? It's not working the way I was hoping it would. Anyway, let's say we had another number. That worked. Let's say we had a number that's not on the tree, let's say 9. Can't believe I don't know how to use paint, it's quite pathetic. Okay, so 9, is 9 equal to 8? No. Is 9 less than 8? No. Is 9 greater than 8? Yes. So we pass it down to the next node. So then we say, is 9 equal to 10? No, it's not. Is 9 less than 10? Yes, it is. Well, then we should pass it on to the right node. But as we can see here, there is no right node. So therefore, we know that it is not on our tree. Okay, and this is like how we find things in a tree. On the other side, what about if we wanted to add something to a tree? What if we wanted to add 9 to the tree? Well, again, similar idea. So first of all, we want to say, is the root empty? If the root is empty, then the root becomes 9. If the root is not empty, then we pass it to the root and we say, is this less than the root? And it says no. When we say, well, then is it greater than the root? It says yes. So then we pass it down. And then we ask the same question. Is 10 equal to 9? Nope. Is 9 less than 10? Yes. Okay, then we pass it to, oh, there's nothing here. Well, in the case that there's nothing here, well, then what we are going to do is we're going to add a new node in that place. Boom, boom, boom. Doesn't work great. There's a green line somehow. Pretty terrible. But then we're going to add a new node into that space. So if it's empty, then we add it there. So we keep repeating until we find an empty space, and then we add it to the node. Now what we're going to use here is something called recursion. Now recursion's not super easy to get your head around, but it's okay. Let's say we have a group of people. Okay, let's go with this rather overly happy bunch over here. I think going to be the best one. Yeah, okay. So, I have no idea who these people are. I assume they're just actors and stuff. But let's say they all have some work to do. If you would kindly be less fuzzy. Oh, I guess not. Okay, anyway, let's say that this girl is called, I don't know, Jane. Now, Jane is the boss. She is the leader of the group. Yeah, it's much better in that picture than it is in mine. Slightly annoying. Okay, doesn't matter. Ah, here we go. Okay, so Jane here, or I don't know, maybe Jopwell, whoever this is. No, that's the company name. Anyway, Jane here wants to do some work. But in order to finish her work, she has to get some information from this guy here. Let's call him Charles. These are all way too British. They're obviously Americans, but still. Okay, so Jane asks Charles to do something. Now, Jane cannot complete her work until Charles has finished his work. Now, she said, go get me the price of, I don't know, gold in Colombia. Who knows? Okay, and she passes it to Charles. And she says, Charles, go find out the price of gold in Colombia. Now, Charles does not know the price of gold in Colombia. So he passes it on to Anne-Marie. Again, ridiculously British names for some reason. And he says, Anne-Marie, do you know the price of gold in Colombia? Yeah, now he can't finish his work and she can't finish her work because the third person is working on it. She doesn't know. So she asks, Brad, because obviously American. Okay, so she asks Brad, do you know the price of gold in Colombia? So now we've got 1, 2, 3, 4 processes happening, and nothing can continue until somebody gives the right answer. Now let's say that Chad just happens to have some Colombian connections, and he says the price of gold is, honestly I have no idea how much gold costs, half $1, no, $1, okay? Brad reports back to Anne-Marie, $1. So Anne-Marie can now finish her work, and she can then pass back to this guy, whose name I forgot, and say $1. He can finish his work, and then pass it back to the original person, who can say, I've now got that information, I can now finish the rest of my work, and maybe pass it back to, I don't know, whoever this is over here, customer over here on this side. And that is kind of recursion. Because basically what's happening is they're all doing the same thing. They're all trying to find out the price of gold in Colombia. I don't know, does gold change from country to country? Who knows? Anyway, so they're all trying to find out the price of gold, but nobody can complete. Everything's passing it down a level to the next thing. Now, there are some basically rules of recursion. That you do need to know. Okay, so it must call itself. So this is a function that's going to call itself. So these are all doing the same thing. So imagine they're all instances. So they're all calling themselves within each instance. It must have a base case. So the base case is like the price of gold. Yeah. So the final case that we get to over here is the base case. And then it must change its state and move towards the base case. Okay. So in this case, the base case, we're going to keep moving, down the way first, and then back up the stack. So everything is this is waiting on this is waiting on that, this is waiting on that. But these are all doing the same thing. They're all trying to find out the price of gold and then working back from there. Not sure if that's going to help at all, but who knows? Maybe it will help some people. Anyway, let's get on to the actual coding for today. So, oh, sorry, this was from a failed version. Okay, so we already have our word node. Now I've changed some things in here, just so you're clear. I've removed all the private stuff. I've left in the getters and setters, don't need them, but I've left them in. Okay, but that's the only big change I've made, and actually, I don't need to have this main stuff going on down here. Okay, so my node is now independent. So, now I need to make a tree. So I'm going to make a new Python file, and I'm going to call it word tree. Now, can you remember how I wrote the constructor last time? So if you can, pause the video and see if you can remember how to write a constructor. What is the top line of the constructor? Assuming you've restarted, so we do def underscore underscore in itself for our constructor. And then each item inside of here, now at the moment, the only thing we actually need at the moment is going to be the, it's down here, isn't it? Is going to be the root. So we need to keep track of the root. We might need to keep track of other stuff later on, but our word tree is more or less just like a starting point for other stuff. So I'm going to say self.root, and for now it's going to equal none. It's going to be empty because there's nothing on our tree. And that should be enough, oops, that should be enough to get things started. Now, probably the first method we want to add to our tree is how to add a word. And again, when I say a word, I mean a word node. So I'm going to def add bracket brackets self comma word underscore node. Okay, so what's the rule here? So I've got my root, but my root is empty. So what should the first line of code in the add be? I should say if the root is none, then if root, self.root, let's forget self. If self.root equals none. Now, PyCharm gives me a bit of a weird thing here I've noticed before. I would write it like that, but it wants me to say that. Why? If somebody knows, please write in the comments. Okay, so if the root is none, then we want to say self.root equals word node. Yeah, so in this case, if there's nothing in the first space, then the first item we add will become the root from now on. Okay, however, if the root has something, we then have to decide, are we going to look to the left or are we going to look to the right? Now, at the moment, our node class does not have left and right. So let's go and add that in to our word node. Oops, I've done it here already. So there was a failed video beforehand where I mucked stuff up. So self.left equals none, and self.right equals none. Okay, so these are going to be the pointers to the other nodes on, oh my god, I can't find anything today. These are going to be the pointers going to the next nodes down. Now, A-level is weird. It does a lot of its stuff as 2D arrays, and I will come back and do a video on how to do a binary tree as a 2D array. For now, we're going to do it the proper way, and the way I think most people in industry would do it. I think it's actually probably easier to understand the more modern way, because the root is going to point to the node is going to point to the other node. It makes a lot more sense. However, you might get a question in the exam that gives you the pseudocode for a 2D array, and then you have to do it their way. Now, talking to the exam board, for Cambridge at least, over quite some time, I have been reassured that basically, if your answer is correct for paper 4, even if it's not the same, even if it's not using their old-fashioned way, then you should get the points, unless they give you pseudocode. If they give you pseudocode, you have to follow their way of doing things. If they do not give you pseudocode, as long as your answer works, you should get the marks. Again, I'm not super happy with the way that A-level does this. It feels very hidden, very opaque. But that's from multiple messages and emails. That's what I understand. Anywho, okay, so basically we've got left and right. So basically, if this is not empty, we want to add it to this node. So we're going to add in another method to our node called add. And it's going to contain the word node. Okay, now for now I'm just going to stick that as a pass, just so you can see what's going on here. Pass just means don't do anything. Okay, so we're going to have a word tree. Word tree equals word tree. Bracket. Okay, now I want to add to the word tree a new word, but let's define a new word first. Now, to use a word, I'm going to have to bring it into my word tree. Okay, so I'm going to have to import from my word node. So import, not import, from word node, which is the file name, import word node, which is the class name. It's not ideal that these are the same, but basically I'm saying from this file, import this class. From this file, import this class. Okay, so word tree, Now let's make a word down here to add to the tree. So new word equals word node. And then I want the same kind of constructors as before. Do I still have them? No, I deleted them. Yeah. Which was what? Hello. And then I need the script, which is hopefully in here still. Yay. Which is in here. Yeah. And then we need the other part, which is the pronunciation. Okay, so there you go. I have made a new word So now I want to add that word to my tree. So if I do word tree dot add new word, then it should call this function here. So let's see what's going to happen. So add self, ignore for now, word node. Now word node is my new word that I've made here. Is the self.root none? Yes, it is. So therefore, the root node becomes equal to the word node. Now, just to show you that that's worked, let's do a print on the end here. Print self.root.mainline. And it should say namaste, right? Or hello, sorry, not mainline, learn line. Sweet, there we go. So now it should say namaste. Yay, namaste. Okay, so it's become the root node. However, what if it's not? Otherwise, we want to add to the root. Now that doesn't mean change the root, that means give it to the root to do the next process. So remember we had Chad and all these other people were passing it down to the next node and saying, oh, you deal with it. I don't know. So we're going to say self.root.add, bracket, bracket. And what we're going to add? We're going to add word node. Okay, so now if I go back to my node here, and this is, I appreciate this is where things get a bit tricky, is jumping from file to file and other stuff, but that's just programming, I'm afraid. Black lines, okay. So, in here, I now have an add method. Now, at the moment, it does nothing. So, if I were to go to 8, I first want to say, is it equal to 8? So I want to say if self dot mainline equals word node dot mainline. So if they are equal, oh my god, where'd that come from? So if self.mainline is equal to word node.mainline, then, well, I don't want to do anything because it already exists there. I'm just going to print already in the tree. Okay, so let's see. Let's say I try to make another new word. So I'm going to make a second new word after I've added the first, but I'm going to have it as the same stuff. Okay, so I've got two identical words with different names. I'm going to try and add them both to the tree. Already in the tree. What happened? Okay, so we said that the first one here is going to be called, the root is going to be equal to hello. Okay, now the next word also happens to be hello. Excuse me, 1 second. Hello. Now, so we've set the root to be hello. The next word we want to add is also hello. Hello. But they are the same. So I don't want to do anything. I want to say already in the tree. However, if they are not equal to it, then first I want to look to the left side and I want to pass, let's say it's not hello, let's say it is bye, I guess. Let's say it is goodbye. Okay, so bye is not equal to, first of all, the root is not empty. Bye is not equal to hello. So then I need to look at these words. Using the alphabetical order, is B less than H? In this case, yes, it is. And this is done using the ASCII or Unicode values. Okay, so B is less than H, so therefore we want to pass it to the left. If it were, I don't know, zoo, then we would pass it to the right because it's greater than H. So then we pass it down to here. Now, presently, this node is empty. Yeah. So because of that, we just want to assign it to that node there. Okay, so what does that look like in code? So then we want to say if self dot mainline. For some reason, I like to do this the other way around. I like the words that I'm adding to come first. Other people seem to do it the other way. So if the word we're adding is less than the mainline, then we want to get, then we want to check, first of all, is the left node empty? So we want to do, so we want to do if self.left is none, then we want to say self.left equals word node. If it's not none, then we want to just try and self.left.add word node. Okay, so once again, is this one empty? Then add it to this one. If it's not empty, then pass it down to this one and repeat the same process again. Recursion's a little tricky to get your brain around, but with a little bit of practice, you'll hopefully get it. So then what do you think? Could you write the code for if it is greater than the mainline? Maybe pause, try and work it out, see if you can. Okay. This should probably be an elif, to be fair, because if you've said this, it doesn't matter. Both would work, but it just saves a bit of efficiency. So elif, then it's going to be almost identical, right? Elif word node is greater than. Now, actually, even here, we could just have this as an else because it's not equal to, it's not less than, so therefore by default it must be greater than. So we can save ourselves a check here. And then we can say if the right is none, then the right becomes the node that's being added. Otherwise, recursively call the right.add over there. And I think that should hopefully work. But there's only one way to figure it out, and that's to try. So we've added hello, but this time we want to add goodbye. Now, I'm going to keep it as capital G. Remember that capitals and small letters have different Unicode values, so they're actually going to cause you some issues. A la vida. A la vida. It sounds more like Spanish or something. A la vida. Okay. Okay, anyway, so let's try and add in a goodbye. And we want to get the value for goodbye, which is this, or the symbol, or the, what do you call it? You know what I mean. Da, da, da. And then we want to get the pronunciation. Okay. So now, yay, hopefully those have been added to the tree. Good. Now, unfortunately, at present, we can't actually test if those have been added to our tree because we've got no way to see what is in the tree yet. What we'll do though is we will do that in the next video. So this video has been how to adding to a binary tree where we're using nodes and classes. Alright, okay, and we'll do the how to print it out in the next video.